region. He has also got Bharat Gaurav Award for the Meritorious Services, Outstanding Performance and Remarkable Role, November 2014, India International Friendship Society. He has worked as a secretary in the Institute of Electronics and Telecommunication Engineers, Allahabad Center 2016-18. He has awarded by Bharat Jyoti Pushkar 2018 by Best Citizen Publishing House Delhi and awarded by Glory of India Gold Medalist 2019 by Best Publishing House Delhi. He is the lifetime fellow member of Institute of Electronics and Telecommunication Engineers, New Delhi. Now, the main speaker of the session, Dr. Ganesh Kaushik. He, who is the scientist F at DRDO at Solid State Lab. He has joined DRDO in 2004 after completing B.Tech in Electronics and Communication from Delhi College of Engineering. He worked in design, modeling, and simulation of CX band, MMIC, and MIC circuits. Later on, he finished his PhD from CARE IIT Delhi on the effects of defects in ALGAN GN high electron mobility transistors. Currently, his interest includes deep-level transient spectrography, temperature-dependent S-parameter simulation and modeling using Silvaco's Atlas and AWR microwave office thermal IV CV measurements and modeling. He has published more than 20 research papers in national and international journals and conferences. He is the renowned peer reviewer of major publication houses AIP, IOP, Elsevier, IEEE, and Taylor and Francis. He has received international recognition by getting a place in the list APL Top Reviewer 2017, IOP Outstanding Reviewer 2016, IEEE Golden Reviewer many times. He is an advisory board member of IOP Journal of Physics, the Applied Physics. He has applied he has also supervised one PhD thesis in collaboration with IIT Delhi. Now, I would like to invite Dr. Ganesh Kaushik sir to commence the webinar. Welcome, sir.
Yeah, good morning to all. Thank you, Ms. Samita, for nice introduction.
Thank you, sir.
Hello, Professor Yatendra. How are you? Yeah. Am I audible?
Yes, sir, you are audible.
Okay, let's start. So, I'm giving this webinar on your college first time. Thank you. I am very thankful to actually Mr. Prince Mishra. Actually, he your student, finally student I think. He came to me for a training program, for summer training, and he was so enthusiastic that he asked me, sir, could you please give me a lecture in my college on your means I'm working in semiconductors, basically electrical characterization. So I promise yes, I will. So today I'm here, and I think the audience is mixed. Some of the electronics, some are the new one, and other branches also, other than electronics in the audience.
No, sir, only electronics and instrumentation.
Okay, okay. Then everyone can follow me. I will start from the basic, very basic of the semiconductor physics, and slowly I will build up to my topic, which is the on GAN hands. So I'm continue. Is it visible? Is it visible? Presentation?
Yes, sir, it is visible.
Okay. So actually, if you look everything around in your life, you will see
Ganesh, sir, your voice is not audible to us.
Hello, now it
Yes,
is
sir.
audible.
Yes, sir.
Okay, okay. So I have switched off the camera because that speaker was little far. Now it is fine. So if you see everything around in your life, you see that one thing is common. There are chips to control your communication, the automation of those devices. In fact, these aeroplanes are also made with semiconductors. The slide is changed on your screen.
Yes, sir.
Okay. So can you tell me who laid the first brick of semiconductors in the world? Any guess? Anyone in the audience can type in chat box. Any guess? Okay. So you will be surprised to know it was Professor Jagdish Chandra Bose in India, Calcutta. He demonstrated the first world RF communication at 60 gigahertz in 1897, and he anticipated that N-type and P-type semiconductors are possible. And he was the first person before Marconi who successfully demonstrated the RF communication to detonate a bomb from a distance. And somehow he was so ahead in time that Sir N. Mott, he's a renowned physicist in semiconductor. He acknowledged that J.C. Bose was at least 60 years ahead of his time. So, being an engineer in electronics, we should know who laid the foundation of this electronics, and it was in our India. And I think most of us are either not aware of this, or somehow this point is missed in the communication or in the teaching or everywhere. So I keep this slide as a first, and I dedicate my all talk to this a great scientist who laid the foundation of semiconductor in India. Now we are asking the developed countries to give us technology, but it was started here on our soil, and that too before independence. So today, my yes, so today actually this webinar is divided into two parts. My topic is effect of deep and shallow traps on DC and RF performance of Algan-Ganham. In part one, I will cover basics of semiconductor physics and traps. And I know some of you can say what is these traps. So I will explain slowly. So first we will discuss semiconductor basics, slowly build up how the PN junction device, a simple PN junction works. So this is the outline of my talk. So it will be first introduction, then crystal structure, what is the role of crystal structure in semiconductor especially, and how energy bands are formed, and how carriers behave in these crystal structure and energy bands, and how they transport on application of field. And there is a trap term I have used that actually explained by Shockley Reed-Hall, SRH recombination and generation mechanism. And I will explain a little bit of basic PN junction device operation. And I know all of you have studied this PN junction device, or maybe will study some of them who have not. So these are the references and books actually I will be referring to from where I have taken this material. So you can note down these books and can read yourself in detail because I will touch just basics. So if you see the periodic table, you can divide the materials based upon their conductivity. As an electronics or electrical engineer, we are interested in the conductivity of the material. So you can divide in three major groups: conducting, semi-metal or semiconducting, and insulator. So in conductor, the freely electrons are available, there is no band gap, and the conductivity is very high, resistivity is very low. In insulator, there are no free electrons. All atoms are bounded, means whatever the electrons are available, they are bounded to their native atoms. But in semi-metal and semiconductor, there are two different terms and that are very useful. And we use especially semiconductor. Although the conductor is the synonym of metal, but semi-metal is a different group. In semi-metal is a metal at 0 K, but semiconductor is insulated at 0 K temperature, means absolute zero. The semiconductor becomes an insulator. But how you differentiate? We can't differentiate the different material based on the conductivity alone. So we need some better definition. So see the group here. I have highlighted by the red lines. We are interested in these group 4, carbon, silicon, germanium. Silicon, everyone know, germanium is a semiconductor, silicon is a semiconductor, but where you will put carbon? If you see carbon in graphite is a conductor. If you see the diamond, you can say it is an insulator. Its band gap is very high, but when you change the conductivity, it becomes semiconductor. And there are group 3 metals, semi-metals, group 4, oh sorry, group 5, and the combination of this group 3 and group 5 and group 3 and group 6, the compound semiconductor can be made. So these aluminum, silicon, uh, phosphorus, selenium, gallium arsenide. Gallium arsenide is one example. Gallium nitride is another example. Indium antimonide is another compound semiconductor example. So, how to define that? Which is a semiconductor, which is a metal or conductor or semi-metal? So, as I discussed, where you will put carbon, it's a metal, semiconductor, insulator. My answer is it depends in which form it is available, what is the crystal structure, and how you have fabricated or grown it. So if you ask me what is a semiconductor, I will tell this is the control of conductivity. In which material you can control the conductivity as per your requirement is a semiconductor. In which you can't control, that is not a semiconductor. It can be categorized in other categories, but not the semiconductor. In semiconductor, we are interested in the material where the conductivity can be controlled as we want. So there can be elemental as well as compound semiconductors. But what is the role of crystal structure? As you can see, the carbon, the electron is an electron, but electron is graphite is different from the electron in diamond. So even the material is same, the morphology is different, and the crystal structure is different. That makes a lot of difference. So that force us to think then how to study these semiconductors, or how to study the electrons or whole, which are the charged particle or conducting particles in our case. So we have to look one by one. So next slide will be this semiconductor crystal structure, because the crystal structure is very important. If you see, if you look how the charged particle will behave. So how they are formed. First, we we have actually invented in the nature. There are different crystal structures are available, and there can be polycrystalline, amorphous, and crystalline. In crystalline also there are different lattices that we will see later on. There are different types of crystalline, but if you see, these are available in the nature, and when we look at those properties, if you talk about Professor J.C. Bose, actually he worked on galena, that is a lead sulfide naturally occurring crystal, semiconductor crystal, and he from there he anticipated that N-type and P-type semiconductor can be made. So, as a human, when we see the nature, we learn from that and we use our technology, our resources to make that useful, and we control on that properties of that material. So, this is a polycrystal. There are small crystal, very small portion, but very large grain boundaries. In amorphous, there is no order. There are disordered atoms, so no orientation. But in crystalline, there is beautiful orientation. But when you talk about semiconductor technology, we use word epitaxial and crystalline differently. Although epitaxial is also a crystal and crystalline is also a crystal, this word comes from. So what is the difference? Actually, if you talk about epitaxial layer, it's a thin layer and a high quality crystal. Means if we compare to a crystalline material, the quality of epitaxial layer is much higher. In crystalline, there can be defects, and they can be grown on a thicker scale. Means uh, uh, crystalline material are used to make substrates. There are several hundred microns. But if you talk about epitaxial layer, on which actual devices are made, that are in nanometer that you can't see by your naked eyes. So it is important to understand what is the difference between epitaxial layer and crystal layer. So what is the need of substrate? Why we need 200, 300 micron substrate to fabricate a device on a few nanometers thick layer or epitaxial layer? Actually, we need some supporting layer or supporting base so that we can process our devices. Later on, we can remove that substrate or we can etch partially to take the advantage, full advantage of that material. So there are different growth mechanisms by which you can grow epitaxial layer. There are different mechanisms where you can grow substrates. There are bulk crystal growth material for substrate. For epitaxial layers, there are molecular beam epitaxy or metal organic chemical vapor deposition system. There are different one. Physical vapor deposition system also there. So there is a difference. So I will not go into the detail of that layer fabrication. So I will study that. I will present this how this crystal structure will affect the properties of the material and how they are useful and how we can take advantage to make a device. So if you talk about silicon, silicon is having a diamond structure. Diamond structure is that in which two FCC lattice means face center cubic lattice. There are different types of simple cubic and body center cubic. There's a face center cubic. Face center cubic means in a primitive cell there are electrons at all eight corners, and there is, sorry, not electron, atoms on all eight corners, and there are six faces and each face is having one atom. And when two interpenetrating abscisses are there, they are shifted by a by 4. A is a this atomic distance between the atom that we call lattice constant. So they are shifted by a by 4, and that's how their tetrahedral structure means one atom is surrounded by four neighboring atoms is formed, and that you can see in this diagram. There are other forms. In actually in diamond, if you replace one silicon atom by another atom and gallium and one another silicon by arsenic, means at the same site there are two different atoms, different type of atom, that is called zinc blend. So it's similar to diamond, but the moment you change these atoms, silicon is replaced by a bigger atom gallium or arsenic, sorry, smaller atom gallium and bigger atom arsenic. So the properties of the material changes. And another example in indium phosphide, so that we will see how the which properties is affected by this structure. But all not three found all not all 3,5 compounds are zinc blend. There are one more important structure, that is woodsite. Woodsite also a compound semiconductor. In here there are two interpenetrating hexagonal cross-packed lattices. And this has one more properties. In zinc blend, actually, the size of atoms are comparable. Gallium is not so off from the arsenic, but here, if you take example of gallium and nitrogen, nitride, gallium nitride. So gallium and nitrogen, there are difference in the electronegativity and the size of the atom. So the uh, covalent bond between these two atoms is polar. There is ionicity, and that give rise to piezoelectric properties. So otherwise, it is similar to that tetrahedral atoms structure in zinc blende and diamond, but that gives freedom to engineering the properties for a particular device, and we use in this property of piezoelectric and spontaneous and piezoelectric polarization to make aluminum gallium nitride and gallium nitride high electron mobility transistor, that is HAMT we call it. So it's it is available in the nature, but we have used it. And if you see that this algan ham, before algan ham there was aluminum gallium arsenide ham in 80s, but after 1990s the research started in gallium nitride when LED was first proposed. That later on it was found that a transistor can also be made, and we can use the mobility, high electron mobility we can utilize, and there is a high breakdown field because of larger band gap here. And we have made wonderful devices from this technology. So how this crystal structure will decide the device properties. So actually, to see how device will behave, what will be the properties. So the charge particle, it can be electron or hole. Hole electron, everyone know, I think hole is a absence of electron, but it moves in a valence band. Means when an electron leaves a valence band, a hole is created, and when next electron comes in that place, so from the valence band, that hole is moved to next place. But how these particles will behave? So it will these will behave in two parameters. Who am I? I'm a positive charge or negatively charged electron or where am I? कि मैं कहाँ हूँ? Actually, where am I will be decided from the crystal structure as well as from the engineering. If we have done some layers, we have specifically designed some technology. So that will depends, because the electron is not same. That I have already told you that two electron in different material will behave differently. Two electron in the same material but having different crystal lattice will behave differently. So no two electron are the same. Okay. So can the properties of a charged particle can be changed in the same material or lattice? Answer is yes. Yes, we can change it. That we will see later. So the next, now we move on the how these energy bands are formed and how our carriers, charge carriers are affected. If you recall in class 12, you have studied about the hydrogen atom, isolated atom and their energy lines. So a isolated atoms, of a silicon also behave differently. It has a discrete energy levels that you can see from this diagram on the right side. But if you use some technology and you make a crystal, or so you melt it and you crystallize it in a particular orientation, so the bands are formed. Means initially these discrete levels will merge together and the energy gap is formed. Here at 5.43 angstrom, this is a lattice constant for silicon. There is a band gap is formed. Lower one is valence band, upper one is conduction band. But if you see, can we reduce this distance further uh, and increase the band gap? The answer is yes. If you apply pressure or any other technique, you can, if you reduce that atomic distance, interatomic distance, you can manipulate the band gap and you can change the property of your material. So then how charged particle will be affected? It is affected in all direction because if you see the silicon also, there are three direction, and we see all the analysis we do in momentum space, that is the inverse space, that is 1 by x, yeah, means k, and we call this 2 pi by lambda, means lambda is de Broglie wavelength. So these are direction dependent, and we solve Poisson's equation by quantum mechanics, and we get all these band structures. We will see in next diagram. And the point here is, so charged particle will behave differently in different direction, and that's why we can use engineering to utilize that particular property. And the type of energy band we get when we solve Poisson, sorry, not Poisson, the Schrodinger equation, and their solution are in forms of waves, and that waves we plot, these are periodic in nature with pi by a and 2 pi by a, 3 pi by a, and we fold it from that left diagram to the right one we can make. That's how that energy bands are calculated in semiconductor. These are the from first principle theory, and we get this diagram. This is a 3D diagram that you have seen in the different books. This is the three direction. Gamma is the center one, 0, uh, and left is x, right is L direction. And these are in the inverse space, means momentum space. K space to solve this Schrodinger equation, we have also used chronic Penny model of effective mass, means when an electron moves in the periodic atomic structure, the atomic potential affect the behavior of that charged particle, electron or hole, it can be anything. So that is also being taken care in calculation of these bands. So based upon these bands, we can differentiate direct band gap is the gallium arsenide, indirect band gap is the silicon. Means in silicon, to transfer electron from valence band to conduction band, momentum should change. K momentum is K should change, and while in gallium arsenide there is a direct band gap available. So conduction band minima is directly at the gamma point on the valence band maxima. And there is a satellite valley that we use for gun effect. Uh, that is not a topic of my today's talk. But here we can see that direct band gap means we can extract light. Means when a electron moves from valence band to conduction band directly, there will be light emission that is directly related with the band gap, and the wavelength of that light would be related to the this band gap. But here in silicon it is not possible. The momentum change needs some phonon exchange. Phonon exchange means crystal vibrations. Means if there are vibration, physical mechanism is involved, then there will not be light. So LED application, mostly they are use these direct band gap materials. People can use and that band engineering also to make direct or indirect combination of these to make particular application, but that is a specific case. And the one more thing I want to tell you, this is a right example is gallium nitride. If you compare all three conduction band and valence band solutions of the Schrodinger wave, you see that slope at conduction band minima is different. Is highest for gallium arsenide, minimum for gallium nitride, and silicon is intermediate. So the slope decides the mobility. Actually, it comes from the effective mass. Means effective mass is more of electron is more, and the hole is even more than the electron in GaN. If you see the slope, it's very low in gallium nitride valence band. So here the mobility is also dictated from this band structure. And one more thing we can see from this chronic Penny model in the right side bottom, that density of state means energy spacing initially, if you look at the atom, it is discrete. When we go away, they merge together. So density of state saturates when we move away from the atom. V0 is a vacuum level. If we have to extract electron or charge particle to vacuum level, so we have to apply that much potential. But density of state is something different. I will discuss it later. So now that band is forms EK diagram we have seen in the earlier slide, but as an engineer, as a device engineer, we would be interested only in the conduction band minima and the valence band maxima and the band gap. That is sufficient to see the how the device is working, how electron and holes are behaving. So we plot an electron energy in the upper direction and hole energy in the lower direction, and horizontal x-axis is the distance. So normally you see this kind of band diagram when you talk about bands in your books. So this is very simple version of actual picture, but that is sufficient to explain the behavior of a particular semiconductor in a device. So in this band, if I put a material that has an energy in the band gap, that will change the conductivity of that material. So here are the dopants which you can use in silicon. There are antimonide, phosphorus, arsenic, for to make it a n type, and here these are boron, aluminum for acceptor, yani p type. But if you see that energies are written with their respective atoms, there are 0.045 electron volts, means 45 milli electron volt, 39 milli electron volt. See, so we need a dopant which is ionized, means that should donate their respective electron or hole to their respective bands at room temperature. Room temperature is 300 K, that is 25 MeV. So we choose a dopant which is near to that one. Although it would be better if we use a dopant less than 25 milli electron volt, but near to that will also work. That will be partially ionized. But for calculation purpose or for example, we approximately assume that all donors in the band gaps are ionized or are acceptor are ionized. So they change the conductivity, and that is called conductivity modulation for a semiconductor. This is the most important technological step to make a device, because if we can't change the conductivity, we cannot use it in any device, because its conductivity, change in the conductivity of semiconductor is the main technology. So if you dope it a semiconductor, it can go, it can replace a silicon atom, substitutional, or it can go and sit in interstitial position. So which one is a donor? So in the left side diagrams, when it's a substitutional impurity, so it will behave like this slide. That particular atom, it will go at that energy and will give that electron or hole to their respective band. But if you see this uh, interstitial impurity, that will generate some defect or a trap. Means that will generate an energy level in between, near to the mid gap band or lower or upper, and that will exchange with the conduction band or the valence band, and that will behave like a trap. This is a trap. Means This energy position can capture an electron or capture a hole or release an electron or hole. So generally these are unwanted things. Sometimes we need defects too to change the property of that particular material to suit a particular application. So here I am introducing the word trap. So you can differentiate between a doping and a trap. And one more thing, if you see the atomic density of a silicon, that is around 10 to about 22 per centimeter cube, and here doping we are talking about 10 to about 15, 16, 17, maximum higher 10 to about 18, not above that. No semiconductor calculation is applicable for 10 to about 19. That is called degenerate semiconductor, means alloying started. For the comparison, if you want to compare any material in front of you, you see that atomic density is 10 to about 23 per centimeter cube, but air where you are breathing is around 10 to about 20. In three order difference, the nature of the material changes so much, and here we are talking about further three order downs doping. See, so the amount of dopants is negligible. If you talk about percentage, it's negligible. But that due to that small amount, the change in conductivity is appreciable. And that's why doping in the semiconductor is the main thing, the main technological parameter. And so we have to just remember the order of the doping and order of the atomic density. That is very handy when it comes to the calculations or to imagine what will happen when we add something or we add something somewhere. So the change in the conductivity can also be done by applying electric field, changing the temperature and radiation. So I will cover the temperature and electric field. Radiation I will not cover in this talk, but you can read from the books. So the to calculate the conductivity of a particular material, so what we need, we have to define a Fermi level. What is a Fermi level? It's a 50% probability of finding an electron. At t equal to 0, if you see the Fermi direct function is plotted in the right side, there is no electron above this EF, but at higher, as you go higher temperature, there are certain electrons which go above of the Fermi level, but the definition remains the same. There is a 50% probability of finding electron at EF, that is uh, Fermi level. So if you talk about the intrinsic semiconductor, where that Fermi level lies, some people will say this is in the mid band gap. No, it is not in the band gap. It is near to the mid band gap, and the shift is decided by the density of state. Density of state is like a chair available in the class to sit to the students, and how many students can sit depends upon how many chairs are available. So density of state is like the chairs for the students, the chair for electrons means how many electrons can go there. Beyond that they can't go because there is no state available. So, depending upon the which conduction band or valence band have higher the density of state, that delta of shift from the band gap will be decided on that. And we call this Fermi level is actually a chemical potential. Chemical potential is the potential in the naturally occurring materials. And we have seen the best example is the battery, the chemical cell. If you see the potential difference between the two half cell or electrodes, that difference is chemical potential. And that potential we call here is a Fermi level. And no, in a one system means which is connected completely, and there is only one system that can have one Fermi level. So Fermi level will not be different in a equilibrium condition in a one system. In non-equilibrium condition, they can be different. So how to calculate how many carriers are available for conduction? That we will do how much dopant we have put in that material, 10 to the power 16 per centimeter cube or 10 to the power 17. Again, which material we have put, what is the energy position of that dopant, and we have to calculate what is the Fermi function at that particular temperature, and we multiply it with the density of the state, and that gives the number of charge particle available. Here is the example of electron in the conduction band. Similarly, you can calculate for the hole in the valence band. But if you see that n dot p means in a particular material, if you increase the doping of n type material, it will reduce the number of hole, because n dot p is always equal to ni square. Ni square is the intrinsic carrier concentration that depends upon the band gap. It's like a zero for that particular material. Why I call this a zero? Because this is mass action law. When a positive charge meets a negative charge, they neutralize each other and some energy is released and they become neutral. So it's like a zero. But this zero is different for different material, because that depends on the band gap, and so that's why when we calculate Ni from the band gap, it is in the order of 10 to the power 10 for silicon. Oh, sorry, for germanium, 10 to silicon, 10 to the power 10 is for silicon, 10 to the power 6 for gallium arsenide, and 10 to the power 13 for germanium. But when you calculate for large band gap material like gallium nitride, it is 10 to the power minus 10. So you will say 10 to power minus 10 is nothing, is zero. But if you ask me what is zero, so I will say in engineering or in science, nothing is zero, nothing is infinite. A number can be zero for some application, but can be significant for another. Similarly, 10 to power minus 10 is zero, 10 to power minus 20 is zero for even higher bandgap material. So it depends on the application or which material you are using, which case you are using. So, if you see this diagram or earlier one, this one, which is the deepest level of that energy in the band gap. So, deepest is the center one. Shallow, shallow means it's near to the bands. Any is either conduction or valence band. And shallow we define from the thermal energy. If it is compared to the thermal energy, means 25 millielectron volt, it's a shallow energy level in the band gap. It is if it is near to the mid band gap, it's a deep level. So if you calculate the band gap of and mid band gap of 1.12, around that is 0.55 electron volt, and you convert in the temperature is huge, means thermally you can't excite a carrier from mid band gap to the conduction band, so you have to choose any other method. So that's why we call it deep. It's a very deep energy level in band gap. So carrier concentration in equilibrium is the function of doping density, dopant energy in the band gap where it is. It's partially ionized or fully ionized, and what is the band gap and what is the temperature at which you are working. So this is the formula. Once you define Fermi level, you can calculate how many electrons are available, what is the electron density, what is the hole density, and all other formulae are written in the books. You can calculate. So now you are comfortable that you can control the conductivity and you can calculate the carriers in that particular semiconductor. But these equations are valid for non-degenerate semiconductors only. Non-degenerate, I am saying again, is a semiconductor on which the doping density is less than 10 to the power 19. 10 to the power 19 above that, or 10 to the power 20, it starts alloying. There is a difference between doping and alloying. Alloying is defined in terms of percentage. Alloying change the crystal structure. Alloy change that particular material. Means when gallium nitride material we mix with aluminium, it becomes aluminum gallium nitride, or gallium arsenide when we alloy with aluminum, it becomes aluminum gallium arsenide. It defined in terms of percentage, suppose 30%, 20%. So it is not doping, but when we dope silicon with phosphorus or aluminum with the 10 power 16 or 17, then this is called doping. So there is a difference, and these all semiconductor physics equations are applicable for non-degenerate semiconductors. So if you see the temperature dependence of the conductivity, when we increase the temperature for a for silicon, gallium arsenide, here it is shown this germanium, that intrinsic carrier concentration increases. See, you can see there is numbers of intrinsic carrier concentration that depends upon their respective band gap. And if you can calculate for diamond, that diamond band gap is around 5.4 electron volt, and that is exponentially related with the Ni intrinsic carrier concentration. So it will come around 10 to the power minus 20 or smaller values. So you can always see that how many intrinsic carrier concentration is there and how that particular material is affected from the increasing temperature. So at room temperature, it is these are the numbers, but when you increase it, you see that intrinsic carrier concentration increases significantly, because this is again an exponential function of the temperature. So what happens when we increase the temperature? That all semiconductors which is doped or undoped, they becomes intrinsic. That happens because their band gap narrows with the increasing temperature due to the energy level shifting, means there is a lattice vibration increases. Actually, if you see, everything around you is vibrating at this temperature, that is sitting, we are sitting around 300 K. This vibration stops at 0 K, but above that temperature, everything is vibrating. We cannot listen it because that frequency is out of our range, audible range. But when we increase that temperature, we feel the effect. So that crystal structure, that energies are disturbed, so band gap narrows, and Fermi level, if it is doped, and then depending upon the how much concentration is there, Fermi level is shifted towards the middle. So every semiconductor become intrinsic. However, it becomes useless also. But wide band gap material can work at the higher temperature. So because their intrinsic carrier concentration is to start with negligible, so to make them appreciable, we need much higher temperature. So they are useful in high temperature applications. So then carrier we can generate with the optical light also. Actually, the band gap is directly related with the light emitted from that material in the direct band gap semiconductor, and vice versa is also true. When we give the energy of the light is equivalent to the band gap by this relation, the wavelength of this energy, then we can excite the electron from the valence band, and they will reach to the conduction band. This electron hole pair generation will absorb that light, and we will come to know what is the band gap of that material by this experiment. This is a simple experiment and very powerful. Here we can measure the band gap of any semiconductor. So next we shift to how to now carrier are generated. We know the methods, how they are generated, how they are moved in the presence of electric field. So we will see now. See, if there is no electric field, the in case of electron or hole, here the case of electron is shown. There is a random movement of in absence of field. The moment we apply electric field, still they are random, but net movement is in a particular direction. Depending on the direction of field, electron will go opposite direction of the electric field, means toward positive side. But here that mobility of that carrier is also decided. See, more easily one can move is the more mobility of that, more mobile of that particular particle is. So Who is more mobile, electron or hole in a semiconductor, and why? I have explained you earlier in with the relation of the effective mass, but you can see the same thing from a different analogy. You see that conduction band is empty in normal case, or if you dope it again, it will be partially filled. Lot of space are available, but lot of energy states are available to occupy the electron. So we can compare that electron in a conduction band is similar to the a student in the empty classroom. He or she can sit anywhere swiftly, so that mobility is fast. But whole you compare that class is filled with the students and one chair is empty in between, and new students come and he or she has to sit there, so that it will take time. So the similar analogy exists, that will define that whole is less mobile. So whole you can compare because here with the filled classroom, because here the whole is the valence band. Valence band is a field full of electrons. There are empty space available, and every electron tries to move there. So there is a attraction repulsion between those particles. That's why we get smaller or lower mobility in case of hole. I think this example of class will remember you easily. Okay, so next is the temperature dependence of that mobility. So when we dope a material for a particular impurity and we change the temperature, if we reduce it, actually that dopant is having an energy that I told you. It is around in 25 millielectron volt, and when we reduce the temperature, suppose 80K or 0K, even 0, but if we go 50K, it is 5 MeV, 10 MeV. That dopant takes electron hole back from that valence band or conduction band, and that's why impurity is scattering when that charged particle moves. The attraction towards that native atom increases, and scattering reduces the mobility. And what happens when you increase the temperature? That lattice vibration increases, and that disturbs the movement of the path. Actually, if you see any crystal structure, there are a lot of space available between the atom. That is vacuum. You can equate with the vacuum, and particle moves from there. So that's why this mobility is always effective by that charge of that atom which is in the on the way of movement of that particular particle and the lattice vibrations. So that's why we get this type of temperature dependence of the mobility. Next is that how this mobility and diffusivity is related with each other, and how it is related with the carrier density. Means when you increase the doping density, your dopants are more, so the attractions and repulsion will be more, so mobility reduces. But what is the role of diffusivity? Diffusivity is the concentration gradient. Diffusion happens due to a concentration gradient, and we have Einstein relation of d upon mu equal to kT by q or kT by e. E is the electron charge. So this is a formula. We have to just remember it. So that's how diffusivity and mobility are related. Mobility comes into the picture when the electric field is applied, and for diffusion, no electric field is required. Only concentration gradient happens either due to non-equilibrium condition, means light has generated some excess carrier somewhere, so they will diffuse, or you have applied some potential and excess carrier has come, so diffusion will take place. But directly, if you see that mobility is the main parameter when electric field is applied and current is controlled by the electric field. But indirectly, diffusivity is also related with the mobility. So diffusivity also plays a role in the current. So we have to calculate these two parameters of the current in all calculation, diffusion current and the drift current. Mobility will give the drift current due to electric field, and we have to calculate total current. So what will happen when we apply electric field in a semiconductor bar? There is a Ohm's law. This is a modified Ohm's law, you can say. J equal to sigma E. Sigma is conductivity, is the electric field, and J is the current density. And that related with the that resistivity is 1 upon sigma, means conductivity related with the carrier concentration and their respective mobility. You can see this formula, and if you see the band diagram in the bottom left side, you see the when we apply that electric field any voltage, the band are shifted, not shifted, band are having a slope related with the applied field. Means the slope of this conduction band on applied electric field will be directly related with the applied voltage, and that's how we calculate that how electron will behave and will behave, and respective Fermi levels are also aligned with their respective bands. So this is the simple experiment when we have a semiconductor bar of finite length, thickness, or area. So when we do this experiment, we can calculate the resistivity of that material, and we use this to calculate the mobility from the Hall measurement system. This mobility we use from the this electrical measurement system, that is Hall. What we do in addition to measurement of that resistivity or conductivity by applying electric field and measuring the current, we put this bar in the magnetic field, and due to this deflection of electron and hole in the one direction, we get Hall voltage on different faces, and we measure that. That gives the polarity, means N type or P type, or and give us the applied voltage directly. How much is the concentration of doping in that particular layer? So practically, we don't use this two probe method. We use four probe method. Means we excite that bar from two electrodes and measure the Hall voltage from different two electrodes, and we exchange all electrons one by one, so that mobility is measured in all directions, and that is a very powerful tool we generally use in our semiconductor labs. So now we have to calculate total current in this a semiconductor bar, or it can be a device also. Always we have to calculate both component, that drift and diffusion. Drift is due to electric field, diffusion due to concentration gradient, and by this formula, using this, we can calculate total current in a semiconductor. And always there is a continuity, means the rate of change of electrons or hole is directly dependent upon the how much is the concentration gradient of that electron in a particular layer, and how much is the generation and recombination. I am using two new terms here. What is means generation will generate the electron or hole, and recombination will recombine, will destroy them. So what is the generation rate minus recombination rate, means what is the net charge available, and what is the total this current density changing with the position will give the rate of change of electrons or hole in a particular condition. This current continuity equation is used to solve this rate equations when we calculate potentials and other parameters from the Poisson equation. So how that thermally carrier are moved. So this is the band diagram. There is a barrier, and there is a dopant. Means there is a highly doped N layer of semiconductor layer, and when temperature is increased particular value, so due to that Fermi direct distribution, that electron can cross that barrier. Means here is the chi, is the electron affinity of that particular material at that particular temperature. If you cross that, carrier can cross that temperature, we can we get the conductivity, and this we call this a thermionic emission, and that is a very useful phenomena when we analyze metal semiconductor contacts, means Schottky diodes, and I think we should call it a Bose diode. He was the first person who demonstrated first point contact diode in earlier, more than 100 years, 1890s. So next transport phenomena is tunneling. So you have heard the tunnel diode. Is tunneling through a barrier, means electron is a wave function. We can calculate that de Broglie wavelength, and when a barrier of a particular energy is presented or particular thickness, the, there is a finite probability that it wave function will cross that. The moment there is a solution exists of wave function beyond the barrier, so there is a tunneling, means that particle can exist there. That comes from the quantum mechanics. So the thicknesses matters in the most devices, and the tunneling is dominant for the thickness is less than 20 nanometers, and 5 nanometer thickness of silicon dioxide behaves like nothing, means you it's very small quantity is reduced when you tunnel or when you measure between the two electrode currents when a metal is placed. So the tunneling happens, and it is very important phenomena when we are reducing the dimension of devices, just like CMOS technologies. So where the dimension are shrinking, the thicknesses of the insulators are shrinking. So this is the one more important phenomena we have to remember. So I have covered most of the transport phenomena which we have to remember. There is one more form, that is space charge limited currents, that I am not covering, that you can read. That is that happens mainly in the insulators where charging takes place when we apply some electric field. So next I will shift to this generation and recombination. Actually, my title is the deep and shallow level traps. That is defined from the generation and recombination of electron and holes and the particular energy levels. So this is a Shockley-Reed-Hall recombination theory, because these three people have given that theory. So we have to look into that. What is that? Is simple one. Means when you give some light or some energy, the electron from the valence band will excite and will reach to the conduction band. That is called generation. And when free electron available in the conduction band combines with the empty state in the valence band or hole with the valence band, it is a recombination. Actually, this is the band-to-band generation and recombination. And but in case of trap, there is an intermediate energy level between in the band gap, and sometimes they are desirable, sometimes they are not. But in this diagram, you can see the upper two one, that carriers can be generated by either thermal GTH or GL by light, and it can be recombined spontaneously or automatically. No energy is required. But in case of recombination, the light may emit in case of band-to-band recombination. And these are called radiative recombination, and we use this type of property to design lasers especially, and generation we use to make LEDs. So, what is a deep level traps? The most important topic of my talk is what you mean by deep level. Deep level, the energy level, as I told you earlier, these are the near mid band gap level energy states. So, they behave differently in a different material, and depending upon the band gap and how much they are shifted from away from the mid band gap. So a mid-band gap energy level is called deep level trap, and it can work as a generation center, recombination center, or a trap level. So when it is a trap, when it is generation recombination center, that depends upon the probabilities, how much what is the rate of generation of the carrier from that particular energy level, or what is the recombination rate. So it can capture, if you see the lower one diagram, it can capture electron from the conduction band, or it can capture hole from the valence band. It can emit electron to conduction band, or it can do the emission and capture simultaneously with the either with the valence band or the conduction band. So we calculate rates here, capture rates, because this is not a single phenomena; it's a statistical phenomena. So there are rates are available there. So there are capture rate, there are emission rate, and there is a recombination rate. So when capture rate and emission rate are comparable, so that trap level will behave like a recombination center, and we call that a generation recombination center. When capture rate is more than the emission rate, then it is a trap that is capturing that particular carrier. And when emission rate is more than the capture rate, then that trap or that trap is not trapping that particular carrier, but it is emitting. Means it can be ionized or neutral depending upon the charge state, which carrier it has captured, which carrier it has emitted. Suppose a positively ionized trap is there in the band gap and it emits an electron, so it becomes positively charged. But when it captures electron, it becomes neutral. But when it captures a hole from the valence band, it becomes negatively charged. So vice versa also. So there can be many permutation combinations depending upon the situation of that matter on that material and a particular device. We calculate all these parameters. But these are very important phenomena from, if you ask from me, that because I measure deep level traps here and how they will behave. So this is the most important phenomena. Just a minute. Yes, sorry, there was some interruption. So that recombination rate depends on the capture cross section. Now I have introduced one more term, that is capture cross section. Means if you see this slide, there is a diameter of atom. When it emits a carrier or captures a carrier, that diameter also changes, and the effective area in which if electron or a hole goes and captured, that is called capture cross section. So the capture cross section also affects that how much will be the recombination rate and how much carrier are available freely and how much traps are available to capture. So and what is the Fermi level? Actually, ultimately, thermal equilibrium is defined from the Fermi level at that particular temperature or electric field. If Fermi level is above that trap will capture the electron. If Fermi level is below that trap, trap will not capture that electron. Means it will emit. Means thermodynamically, it is not sustainable to have an electron in a trap which is above Fermi level. So recombination rate is also function of temperature in electric field, and this is a simple equation. It calculates the how much excess carriers are generated in the semiconductor materials, and it then calculate the recombination rates. Uh, by these equation we can calculate how much electrons or holes are captured or emitted and how traps are behaving. And we use particular experiment to determine how these rates are. So this is the same thing which I have explained to you. So SRH recombination and generation center. Uh, if you see in the upper figure, that's before this first one, that here that electron is being captured. Here in lower one it is captured. The second one before figure, it's electron is being emitted. In second one, electron is emitted and it is here available in the conduction band. Similarly for the holes, emission and capture. So it is the ratio of this emission and capture rate which will determine that the trap is occupied or not, and how much is the trapped electron or hole density which we are interested, how much charge they have accumulated, and how it will affect the conduction of the electron or hole through that particular semiconductor in that particular region, because that depends upon the region also. Some traps are created in a particular region, some are naturally available, so it depends upon the case. So there are different cases where we have to use these things differently. So you can calculate capture rate Cn equal to sigma n Vth. Vth is thermal velocity, sigma n is the capture rate. Very simple formula, and emission rate is the capture rate multiplied by this exponential factor, where Et is the tap energy, EC is the conduction band energy, T is the temperature. So these are the simple one equations which we can use to determine that particular location is emitting an electron, emitting a hole, or capturing electron or capturing a hole. So these equations are derived from this one, this recombination rate equation. So this is the simpler one. So next, when we learn this SRH recombination generation and how electrons will move in the presence of electric field, how bands are bending in presence of electric field. So now we can calculate how the currents are calculated, or how currents will flow in the junction diodes. So next and the last topic for today is the basic PN junction device operation. Although you have, I think all of you or some of you have read, or more other people will read in the subsequent semesters. But you see, this is a simple device. You can say it's so simple. It's the P-type semiconductor and N-type semiconductor. But if you imagine, if you learn this simple device, you have the master, you become the master of semiconductor technology. In India, as a whole, we are struggling to make a simple p-n junction diode. If you see, all LEDs we are using in gallium nitride, these LED bulbs are imported ones. All other colorful LEDs also are imported ones. Very few devices are made here, and there are specific one to microwave applications. But if you see, majority of the commercial devices are being imported. Why? Because there is a need of money that government is putting now, trying to lure the investors and foundry persons to set up a foundry here. But there is, I think, lack of trained manpower also. So now it is very simple p-n junction diode. But if you see the behavior, if you understand that how the particle is behaving, and you can calculate yourself from the Poisson equation, you becomes master. And after that, you can explain the working of any device, be it a BJT, bipolar junction transition, FAT, field effect transistor, MOSFET, HAMT, anything. So it is very important to learn how p-n junction diode works. So initially, when p-type semiconductor and n-type semiconductor are separate, this is the lower one in the left side Venn diagram of the slide. So you can see the Fermi level in the p-type is near to the valence band, and Fermi level in the n-type is near to the conduction band. When we join them metallurgically, here metallurgically is important because they should be in direct contact, means there should not be any distance between the atoms of p side and the atoms on n side. So that's why this junction is called metallurgical, and without metallurgical junction diode will not work. So what will happen at t equal to 0 means the instant when you join them. So first thing that comes into the mind is there is a concentration difference, means electrons are more on the n side and holes are more in the p side. So hole will move towards n side. In this diagram, lower one you will see in the middle, and electron will move from the n side to p side. So there is a space charge will be created. That space charge slowly build up, and the moment space charge starts building, the electric field comes into the picture. What that does that electric field do? That electric field will reduce or present a barrier for electron and hole, or reduce means stop the diffusion. Means now, when equilibrium condition is reached, a certain barrier between p and junction is formed, and a built-in potential has been created. So there cannot be a movement of electrons or holes due to concentration gradient now, because there is a barrier now. Electron has to cross. Earlier they were moving freely due to just concentration difference. Now there is an additional barrier, and electron and holes doesn't have that, do not have that energy to cross that barrier. But can we measure this potential outside the terminals? Answer is no. Why? Because after that depletion region which is formed where the built-in electric field is there, there is a neutral region, and neutral region there is no potential difference. If we can measure by any specialized technique inside the depletion region, we will get the field, surely we will get the field, but outside that depletion region we will not get any field. So you can use any particular probe, that too in nanometer size, then you can measure this inbuilt potential or inbuilt electric field, otherwise not. So this is the same thing which I explained earlier, that drift and diffusion takes place. That drift is due to that now electric field is maintained inside that depletion region. So that electric field, whatever carrier comes at that edge of the depletion, that sweeps in that direction. So thermodynamically, although I said that here diffusion is stops, practically it is not. That minor diffusion is taking place, minor drift current is flowing in opposite direction. So net current is zero, but inside if you see the picture of a diode, it is constantly changing. There's electron and holes in a very small quantity. Depending upon the temperature, they are crossing this junction, and but maintaining the equilibrium condition. So there is no net charge, no net current. But when you increase the temperature, the number of electrons or holes which are crossing the barrier, that will surely increase. So if you see the right side diagram, in the depletion region, beyond this neutral region, there is a transition region where recombination is taking place. Means the moment excess carrier comes in opposite polarity of means excess electron comes in the p-type semiconductor, excess holes come in the n-type semiconductor, what will be the fate? They will recombine immediately, and that's why that transition region is there. So these are three important regions: the space charge region, neutral region, and the transition region. So if you ask me where is the diode, is the diode only the depletion region, the transition region. Beyond that region is actually not useful, not required. That is there because technical technologically it is not possible to reduce to make the device in that particular direction where we need that p-n junction depletion width, that is in nanometers, 100 nanometers, 200 nanometers. So in the transistor we will see again that we need some distance between the electrodes. That's why we introduce some neutral regions or some spacing. Otherwise, actual device is in the depletion region only, not beyond that. So if you see the picture of abrupt junction, p-n junction diode, abrupt junction is means one side is heavily doped, and the moment we dope one side heavily, the depletion width on that side becomes nearly negligible or zero, and that is the case of metal semiconductor junction diode. So this is the particular case, and here also we solve the Poisson equation with the specified boundary conditions, and we get the electric field distribution, potential profile, and depletion width. That depends upon the doping density and the built-in electric field. So we use this method, particular this depletion width method in the CV measurements, capacitance voltage measurement. Means there is a depletion layer capacitance, means when charge are separated, positive and negatively charged are separated with the distance, that will give us some capacitance. If we can measure it that capacitance, we get to know what is the doping density of a particular device, and that in measurement instrument is here available in our lab, and we do it regularly, and we calculate what is the doping and what is the condition of the dopants, means either they are a p type or n type. So this is the most important after Hall measurement. CV measurement is the most important measurement. Here we can do this CV measurement either by mercury probe directly without making any contact or any diode directly on the wafer. That is a non-destructive technique, or by making some diodes. We uh, do this experiment. So here we need abrupt junction, because in normal p-n junction the depletion width goes in both sides, and the situation is complex, and that equation will not be that be simple. Here, in the case of abrupt junction, what we get from the CV measurements, we calculate depletion width directly from the capacitance, this epsilon A upon D, and the differentiation of, excuse me. Sorry, again, actually there are disturbance from the calls. So this is the CV measurement where we can calculate this topping density. Actually, 1 by c square, if we plot in CV measurement data, we plot 1 by c square with respect to voltage, we should get a straight line. If it is a uniformly doped junction, that is the one parameter that determines that what is the status of the junction is, and the slope of that 1 by c square curve directly gives the doping density by this formula, and this formula is again obtained from the Poisson equation. All the semiconductor equations which are not quantum means means we are not taking energy state in discrete energy states. They are derived from the Poisson equation. The moment we go in the quantum nature of that particular particle, we have to solve the Poisson equation along with the Schrodinger equation. Then the situation becomes complex and more complicated, so we need more resources. But here we can do very simple things. We can get to know what is the doping of a particular material from the electrical measurements. So that's how. The next one is how this diode will behave in different biasing condition. At zero bias, if you can see that band diagram, respective diagrams. And one more thing, as I mentioned, the Fermi level is same when equilibrium condition is there in a particular system, one system. If system is a diode, then it is the same chemical potential. So if you see that there is a built-in potential and there is a same distance in the neutral region from the respective bands of Fermi level. EC minus EF is same, whatever is the earlier, and EF minus EV is the same, what is depending upon the doping of P and N, means P type or N type. So what is the shifted when we make the diode is the bands, conduction band and valence bands shifted, and the built-in potential VBI is formed, and the slope of this VBI will determine how much electric field is generated. So the slope of these bands will directly translate into electric fields. So when we apply additional electric field, suppose forward bias, and P terminal is connected to the positive one, so that reduces that slope. And when we and the depletion width also reduces respectively. And when we apply reverse bias, that slope increases, depletion width also increases. And again, due to that Poisson equations, all the electric field is directly related with the slope of conduction and valence band. But if you see the non-equilibrium condition, forward bias and reverse bias, then now Fermi levels are different. Electron Fermi level and hole Fermi level are different. In non-equilibrium, it is possible because now this is a system in presence of electric field, and in between there is a depletion region where quasi Fermi levels are defined, or you can say quasi Fermi level. So when we calculate these currents, means we have to calculate number of carriers, so we need these quasi Fermi levels. And you can calculate current in a PN junction diode anywhere. Total, because in series total current is same. Somewhere it is a whole current, somewhere it is electron current, depending upon the where you are calculating. So this is the position dependent distribution of the electron and hole current. But if you see, J total remains the same. Either it's the depletion or it's the neutral region or transition region. So normally we calculate all these parameters in the transition region. So here we have all boundary condition, and then we solve for Poisson equation in the transition region. So we have all the parameters, and here drift current as well as diffusion current, all components are there present. So this is the typical IB characteristic that you have seen in many books, and that is current is exponentially related with the applied voltage in forward bias, and in reverse bias the saturation current is almost constant. Uh, Practically we say zero, but it never zero, and neither it's horizontal to the x-axis. It always have a slope. So why these current is flowing in the reverse bias? Actually, in the depletion region also there are many things there which are happening. So there is a depletion reason is there. So electric field already it is there. So due to the thermal effects also, or some due to light also, if you shine a light on your depletion region, the carriers can generate. So carrier can generate and they will be swept by the electric field. So that will give rise to the electric current. In reverse bias, the depletion region width is more, so the carriers are generated, and you get this leakage current or reverse bias currents. Mostly these are unwanted one, and in the forward bias, this depletion region is more. So most of the recombination current is flowing through that device, but in reverse bias, it is generation current. Okay, so this is the measurement how ideal our diode is. Means we have measured the CV characteristic. One if 1/c square curve of that particular diode is a straight line with respect to voltage, that's a one measurement from capacitance point of view. From current point of view, if we take log of current, forward current, it should come as a straight line. If it is not a straight line, means some non-ideality is there. So that non-ideality, if we can measure with temperature dependence and other parameters, so we can calculate how much traps are there, how much they are contributing generation and recombinations by calculating their different generation and recombination rates. That gives idea how traps are behaving. So in diode, particular diode, practically we get around 1.01, 1.02, but it's very difficult to get, nearly impossible to get ideality factor n equal to 1 in practical diodes. So with this, I conclude my today's talk, and I introduce what are the deep levels, traps, and basics of semiconductor physics that I will use in my next lecture. Hopefully, you find interesting. Now, any queries or anything? Thank you very much for your patient listening.
Thank you, sir. It was great hearing you. And those who are having doubt, please raise your hands.
Any question? Hello.
Yes, sir.
Hello.
Yes, sir. Just a minute. Those who are having doubt, please raise your hands. Yes, Ujishita.
Good afternoon, sir.
Yeah.
Sir, I have a doubt regarding what will happen with different crystal system and how will it affect if the level change from Fermi to the other level?
Your voice was cracking. Question. Repeating. You are asking what will happen when Fermi level is changed from one level to another level?
Hello, yeah. Good
Yes,
afternoon.
sir.
Thank you for nice lecture. Actually, she is asking, uh, can you tell your name, please, students?
Yes, ma'am. My name is Ojaswita, and I'm from Electronics
Okay,
Department,
okay,
first year.
yeah. Ojashuta. Sir, Ojashuta is asking what will happen with the different crystal structures.
What will happen with different crystal structures? In what conditions? Hello. Hello. Hello.
Hello?
Yes,
Uh,
Actually, what will happen in a crystal structure? After that, I could not listen. What will happen?
Okay, sir, she is asking, student from electronics,
Yes.
is she asking that what will happen with different crystal structure system, like in earlier hexagonal, orthorhombic, rhombic,
Yeah.
monoclinic, triclinic. So
Yeah.
what will happen if have such kind of structure? She is asking this thing.
Actually, that charged particles will behave differently in all structures, whether it's a diamond, G-band, or bullseye. I presented all these three, and if you talk about other crystal lattices, so everywhere the band structure means EK band diagram will change, and the behavior of that particular or electron or hole will change. See, the mobility, the density of the state that directly calculated from the crystal structures by solving the Schrodinger equation. Have I answered your query?
Now Jashita is clear. I think other student he is asking that what will happen when means level will change from Fermi to other one. One more question from other student.
Which level?
Hello.
Which level is changed from Fermi to other one? Level of what?
Means sir, his question was that like if level will transfer from each other, other means like for me to other, other to for me. What if transition is happening like that? Then what will happen?
Transition of electron.
Yes, yes.
I
They are.
assume that he or she is asking about that trap level is available exactly at the Fermi level. So, if this is the question and transfer is taking place between the band at that trap level, depending upon the which trap or which side Fermi level you are, electron or hole. So that exactly at that level, the generation recombination will be equal. So it will behave like a recombination center. But if Fermi level is little bit moved above that trap level, that trap will be occupied, and below that trap will be empty. Have I answered the question, or it was something different?
Hmm. Okay. Sir, one more question is come from here from one of the student. Student, can you ask your question by yourself?
Yes, Navneet, ask the question.
Yes, sure.
Good afternoon, sir. Myself, Noni Dubey. I am from electronics second year student. So my question is, why do we focus on study of deep level traps, not on the shallow level traps?
Navneet, very good question. Actually, shallow level traps is nothing but a dope tank. Actually, we start the semiconductor lecture from the doping only. So all the shallow level traps normally are the dopants. Because if you take the example of gallium nitride and p-type gallium nitride is made from the dopant level that is 200 milli electron volt away from the valence band and still normally 2.2 electron volt is a huge energy and it's a deep level, but here it is a dopant. So shallow level comes under the category of dopants, but deep level are something different because here is I have introduced the rates, generation rate and recombination rates. So timing is also important. The shallower levels are faster in nature, means they capture or emit electron very fast, but deep levels, they have a very large time constant, and depending upon how much energy, each energy level they are, can be in hours or days. So that's why deep levels are important. And I will tell you in the next lecture that the role of deep level in particular gallium nitride hemps, that is very important. And we have a specific instrument to measure these deep levels, that is DLTS, deep level transient spectroscopy. That is done in a transient capacitance method of the diode. And we measure all the variation of transient capacitance and vary the temperature, and we calculate the energy capture cross section of that concentration of those pack. So, but shallow has to be studied by current, not by capacitance, because shallow will give a conductivity.
Thank you, sir.
Yes, Saurav, you can ask. Yes, Akshay.
Sir, my question is this: during manufacturing of chips, if glitches are occurred in the semiconductor, then how it is going to affect the overall performance of the chip?
Actually, glitch means what? Glitch means some malfunctioning in, during processing or a particular step. You are saying?
Sir, I'm talking about like during manufacturing, the effect of environment due to which glitches occurred in chips, or due to some impurities, the glitches occurred.
Okay. Actually, the semiconductor fabrication means ultra clean environment. Means if you talk me, you ask me who is the most polluting part in that semiconductor fab lines, it is humans. Presence of human affects the reliability and yield of the chips. So we don't call it a glitch. We call about what it will happen and the yield, overall yield of that fabricated devices, or the function will not be as intended. So surely anything which is not has been taken care of in the design of technology, something happens, either humidity change, temperature change, or environment change of any kind, or even time change between two processes, it will change the characteristic of your device, either a diode, transistor, or anything. And its reliability is also affected, yield is also affected. Yield means how many chips you can extract from the chip or from a wafer. So, and how is the uniformity across the wafer? So all these parameters are affected. So we have to take care of that. There is no solution. We have to follow the stringent conditions, stringent rules, timings, everything. So that's why this technology is a $1 billion technology. Either we have to make a 50 paisa device,
Okay, sir. Okay.
and
Thank you, sir.
yep.
So there is a question from Akansha Mishra. If any air particles or dust particle are entrapped in semiconductor, then how it will affect the performance?
See, generally when we are again, this is a similar one question which was earlier asked. Anything which is coming inside the layers unwanted, that is not desirable, and its effect will be will surprise the results. Means you will get the result which you will say I have not seen anywhere. So the solution is to control the environment, to control the fabrication. Most of the automation is used that's why in these lines, and the stringent protocols like IETE,
Sir, your voice is not audible. Please don't leave the meeting. Sir is joining us soon.
Thank you, sir. Hello.
Sir, please wait. Sir is coming.
Okay. Hello. Hello.
Sir, thank you for your great lecture for us. And now I would like to invite Yatin Gaurav sir for a vote of thanks.
Thank you, sir. Hello.
Hello.
Thank you, Janesh, sir. It was a very wonderful speech, sir, from you. And truly speaking, that it was a very nice interactions, and hope so fully that the all the participants must have benefited with the updation in the literature review processes and the employing the foundation ground of the electronics, sir, and definitely research problems identification, sir. Hello, am I audible? Hello, hello.
Yes, sir, you're audible.
Okay, okay. Thank you, sir, for your wonderful speech, sir, Janesh, sir. And also, I'm thankful to the Ram Suchit Yadav, sir, that he has undertaken the whole webinar under the as well as the best IERT society in the IIT organization. Thank you, sir. And once again, I would like and very heartful thankful to you also. Thank you, and also thankful to the participants that they have the patience for all this webinar. Thank you.